So let me now introduce the keynote speaker for today, Adam Taylor. He's a world-recognized expert in design and development of embedded system and FPGAs. Throughout his career, Adam has used FPGAs to implement a wide variety of solutions from radar to safety-critical control system and satellite system. Adam is a chartered engineer, senior member of the IEEE, and fellow of the Institute of Engineering and Technology. He owns the engineering and consultancy company Aduvo Engineering and Training. And FPGAs are Adam's first love. He's author of numerous blogs, articles, and books on electronic and FPGA design. So put your hands together for Adam.
Yeah, you give me the warning, right? Perfect. So good afternoon, all. Hopefully this talk is not going to get me sued for using the Star Trek logo. So as I said, my name's Adam Taylor, and I'm going to talk to you a little bit today about how we can use AI in our FPGA design. And I get sometimes that this is a little bit of a controversial topic, or it seems to be anyway when I post about it on LinkedIn or Twitter or something. But it's something that is coming, it's here, and we have to think about how to use it. So I want to ask you a favor, actually, for the moment. I want you to imagine that actually we're in the 24th century, and that Star Trek was real, just for the first few slides, just so we could talk about it. So I want to give it a little bit of framing to it. So over the last few years, LLMs like ChatGPT, Claude, they've generally creeped into most aspects of engineering and of modern life, And there's a lot of hype about it. There's a huge amount of hype about AI and what it can do. And about, must be 2000, maybe back end of 2003, maybe beginning of 2004, I wrote some blogs about what could AI do. And I think I did the three. I think I looked at the time I looked at Claude, Chat, maybe Gemini, or maybe it was Grok, I can't remember which one of the two. Just to make it, basically, can it flash an LED on an FPGA dev board? And all three of them generally could flash that LED on the dev board. Wasn't the nicest way that they went about doing it, but all three of them from a simple prompt could generate me a bit of VHDL and make an LED flash. Fast forward a few years, and actually I find myself as an engineer now focusing much more on defining capability than on writing beautiful VHDL or Verilog. And that's one thing that's kind of close to my heart, because I think the key thing that engineers develop is not writing beautiful code, but is actually delivering capability. So I find that actually these days that the LLMs are they're quite good. If you guide them correctly and use them correctly, they are quite efficient in helping us with our engineering tasks. And we can see this across a range of AI disciplines that we're involved in, from developing boards to doing FPGAs to embedded software, and particularly higher levels of the software stack. So it's moved from something that was a little bit of a curiosity into something that now, if you're an engineer and you're not looking at it, it's kind of like ignoring VHDL and Verilog when we started moving away from the schematic design. Now, I'm getting old. I'm 49 in a few weeks. But I grew up, in the 80s, early 90s, watching science fiction like many engineers did. And there's two conflicting worlds, there's Star Wars and Star Trek. And both of them have some interesting aspects as to engineering and their approach to engineering. Star Wars is a lot times my life has been in the past with engineering projects where you're trying to fix it, you're trying to get something delivered out to a client, get it done. Hopefully people aren't shooting at you, but it's still a challenge to get something done. And there's a little, it's very improvised, and often, it's done in the nick of time. The other one, obviously, is Star Trek. And when I started doing my engineering degree back in 1994, 1995, long enough ago that I can say it was last century now, I would watch Star Trek Next Generation while I was doing some work. And they had some interesting technology and some interesting engineering approaches there where their engineers, Scottie, Geordi La Forge, would basically have a very systematic approach to engineering. They would work out what the issue was, what they wanted to do. They would work out the diagnostics, any simulations, And it was a lot more polished and a lot more cleaner and a lot more systems driven than it was than the other world of Star Wars was. Maybe because one happened a long, long time ago and the other one happened in the 24th century. Maybe there was some engineering involvement along there. But it got me thinking about AI and how we work with this, and if there is any sort of commonality between some of these worlds. And as it's a keynote, I get to have a little bit of fun. So one of the key things about the Star Trek world, that 24th century engineering, is they were conceptually systems engineers. The Scottie, Geordi La Forge, they were systems engineers. And that's something that we really should be as FPGA engineers anyway. Regardless of how we're implementing the code, we really should be systems engineers first, thinking about what's the architecture, what are the interfaces, what are the requirements, how are we going to validate these requirements, and how are we going to deliver this solution. And this is one of the things that kind of comes through in that world, where you see in the Starfleet view, they have to work out what the requirements are. They guide and constrain the computer to their power budgets, their safety margins, and then they review the outputs and they ship it. Now, all of that is wrapped up nicely in 45 minutes because they've got an episode to meet. Real-world engineering doesn't quite work like that. But it's an interesting approach to how it works. And in the real world, until relatively recently anyway, we would do similar things. We would write the specification. So we would write a huge specification document. And that's really important as engineers, that we have some specification, because if we don't know what we're aiming for, we don't know what to develop and how to test it. Then we would go off and we would write every line of code by hand. And I used to love writing VHDL. I'm a VHDL person, not a Verilog person. I used to love writing VHDL. These days, the last 5-10 years, I'm not so keen on it. I like working out the solution and how we're going to get there in the engineering side of it. The implementation side of it, when it comes to sitting down and writing the VHDL, honestly, I find it boring. It's got to that, maybe I've done it so much that it gets to that stage, but what I'm interested in is that capability and delivering that capability to the customer and to the end client and seeing it working. And sometimes we can even talk about that capability that we've delivered to the end customer. Obviously, then you're going to go through the debug stage and you're going to go through the bring up. But one of the key things here is, when I was doing my degree, you were watching Star Trek and you'd see them sort of talk to the computer and the computer would go away and do all the heavy lifting. It seemed really science fiction. It seemed like that world would never come. But actually, that world is closer than we perhaps think it is now. So let's take a little bit of a look at that. So what they were essentially doing in Star Trek is they're working at a higher level of abstraction. They don't skip the theory. They're not vibe coding, but they're actually understanding what they're working on. They deeply understand the physics, the mechanics of how it all works, and they're doing good engineering practice. They're doing system design, they're doing the implementation. But the most important thing and the most important message to take away is they know the theory. They know how it's meant to work, even if it's fictional. And they've spent years and they've done the time building it and working up and climbing up that stack. Yes, they're using abstraction, layers of abstraction, but that is, that is what they want to do to be able to be efficient and work through it. Now this is similar. Let's come back to the 21st century now. This is similar to what we're doing in FPGAs and the journey that the FPGA world has been on. We started this back in the 1980s. We started with implementing with logic equations. We hit a point where the programmable logic gets so big that we can't actually implement with logic equations anymore. So we moved on to schematic design, schematic capture. But even then, eventually the devices get too big. So we can't fill them full using the schematic capture. Well, that's not to say we can't, but timescales and project demands mean that we can't do it. If we wanted to, we could still fill everything with logic equations, but project managers demand that we have to deliver occasionally. So we have to move on. Only occasionally do we have to deliver, not too often. So we started with schematic capture, and we saw that. And then, obviously, the devices get even larger still, and they begin to add more complexity in there. So they move from just being CLBs and lookup tables to having things such as processors, DSPs, block RAMs in there. And we start working with HDLs and developing HDLs because it's another level of abstraction that we can work with. And then more modernly, perhaps 2013 onwards, we see the rise of the modern FPGA, the modern SoC, and we see more flows that are based around HLS and model-based design. Now, I'm a big fan, I'm talking to a few people here today so far, I'm a really big fan of high-level synthesis and model-based design. I think it's very useful when we're developing FPGAs. It allows us to focus on the algorithm, not necessarily the implementation. We still need to know about the implementation because we still need to be able to add the pragmas, the optimizations, the stages there, but it allows us to lift up that level of abstraction and be more productive. And that's one of the key things that we have to do is because, as I said earlier on, we're here to deliver capability. So we have this ability to do HLS, model-based design. I quite like model-based design because it's a little bit more portable than HLS. If I'm honest, HLS tends to tie you to one particular vendor. Model-based design is a little bit more flexible and allows you to target any vendor you want. Plus, I'm quite a visual person anyway, so I like drawing diagrams. But now we find ourselves in this other area of FPGA development where actually the devices are getting larger and larger still. Our timescales, I don't know about you all here, but our timescale, nobody seems to be giving me longer timescales as an engineer. Everybody seems to want it quicker rather than later, you know. Ideally, if I could do it last week, that would be great. If we could get the DeLorean going and do a bit of time travel, then that would be good. Maybe the next talk I give will be what Back to the Future can teach project management about FPGA design. If you hit 88 miles an hour, 88 LUTs an hour, you can go back in time. So it brings in that AI-assisted design becomes increasingly important. But one of the key messages, one of the key things I want to talk about this, where we've gone through this, is actually, while we're moving up the layers of abstraction, and as we've gone through the layers of abstraction previously, the key thing still remains is that you still need to be an engineer. You still need to know the basics, and you still need to know how it works. Yes, we might be moving further away from the actual logic gate, shall we say, because now we've started writing in VHDL or HLS or model-based, but there are times when you've still got to know that. So you've still got to have that fundamental foundational knowledge, and you can't just get away. But one of the things I think is that actually if we do this right and we think about our development right, then AI just becomes another level of abstraction for us in our design and development. So I've been doing this for maybe 6 months or so now, maybe a little bit longer. So I'm going to talk to you about how I've been doing it, and then you can all tell me how I've been doing it wrong, and I can learn something from today. But what we're going to do is we're going to give, when we're working with AI, we're giving it a brief. If we give it a vague intent, in just like the real world, if there's no systems engineering, no requirements gone, back to we're all systems engineers really, if we give it a vague intent in, we'll get a vague design out. That doesn't matter whether we're using an LLM or whether we're using an engineer sat at a bench. If we don't tell our engineer what we want, we get vague information out of it. So a lot of the tools and a lot of the process that I'm talking about when I'm talking about AI applies to how you should be doing it anyway if you're working with teams of engineers. We want to give clear requirements. And one of the biggest things I see as an engineer is very woolly, undefined requirements. Every engineer should have to go on a requirements writing course to learn how to write requirements and to make them good. Because if you've got clear requirements, testable requirements, you know, we can write better code, we can design better systems, we can do it. We also need to understand about the functional and the non-functional requirements so we can put all this into our tool. We want to think about when we do our requirements and that we do that systems engineering, we want to think about our corner cases and our test conditions as well. So I like to think about trying to work out what the boundary conditions are, what the normal conditions are. One of the things I've learned over the years is to tell the customer how I'm going to test and prove each of the requirements. It's absolutely critical to go through each of the requirements that you get on your design and say, I'm going to prove this via simulation. I'm going to prove this via demonstration on the board. I'm going to prove this by analysis. I'm going to prove this by something. And it's really important to do that earlier on because the later that you do that in the development chain, the more likely it is that the customer will turn around to you and say, well, that's really nice, Adam, but actually we wanted it to do it this way. So it's like all the things in engineering, communication is key. And the earlier you communicate your intention, your requirements, and your approach, the easier it is to actually get to the end. And for me, that's important because generally when I get to the end, I get some sort of payment milestone, which is always quite a nice thing to do. So we can think about those test cases, what we're going to do, how we're going to do it. And one of the other things that we like to give is we give them all of the development guidelines. So we all have coding standards, life cycle plans, documentation, review gates that we work with. All of these things we should be passing to the AI and working with the AI. If you were to work with a human engineer, if you were to have a new engineer joining your team, you would give them all of this information. You would give them, here's where we keep the coding standards. Here is where we keep our development processes. Here's our directory structure. Here's where our Git repos are. Here's how we write. Here's the requirements that I've written for you to do it, and here's our review process and our design process. All of these things we'd give if we would give it to a junior engineer or a new person on the team, and all of these things we give to the AI when we're working with the AI to help us get a better quality out and to make sure that we don't get that vague design out of it. So my workflow is quite simple, really. I try to keep it in the real world and how we work it. So generally, I like to define the module. So in that module, I want to define the functionality. Along with the functionality, I want to define the interfaces. I was talking to somebody earlier on, we were talking about the KISS principle, right? So we're all familiar with the KISS principle, keep it simple, stupid. So there's a lot of plays on the words we can do with that. So keep it synchronous, stupid. Keep the interfaces standard. I'm going to write a blog about this. I think it's a great idea. But there's a lot of things that we can do in this module design to make it work. So we can keep the interface, we could define the functionality, the interfaces. What we really want to do as well is define corner cases. Anywhere where something might not work and we might need to recover from that or handle that gracefully, we need to define that. And we want to write it out properly. You know, not on a scribbled note on somebody's desk or something. You know, it wants to be documented somewhere formally. I tend to prefer cloud-based providers for that, but anywhere is good. Now, like many companies, we've got coding rules and rules around reuse. So we want to provide that. And one of the things that I'm really keen on actually is having an IP core library that we can reuse. Obviously, vendors provide their IP core library, but my IP core library is device independent. So we point people to that device, to that IP core library. And there are lots of other libraries about. I know Patrick is talking later on about the pile of codes. There's a lot of other libraries about that you can use in your design to help you do that as well. Once we've done that, I quite like to get it to generate a test bench. It's an amazing thing to do, is to actually ask it to generate your RTL, give it a set of test results that you're going to work with or that you expect out of it or behaviors you expect out of it, and then to sit, normally with a cup of tea and some biscuits, as you can tell, while I watch the AI just spin round and just try to work it through. And you can give it the guidance like you would a junior engineer, although you can swear more at it than you can at a junior engineer. It doesn't get offended generally, or you don't have to go talk to HR anyway. That's the important thing. Now, so far, step one, describe the module. I've written that by hand. I've written the requirements. I've put all that in there. The rules and the reuse, you know, that's existing from having good company process that we've had. So that exists and we put it there. The only bit the AI is actually helping us with at this point in time is step 3, that generate the RTL and the test bench. Once we get that out, though, we have to be a little bit untrusting of it. Just like you would an engineer, you have to prove it and prove that it works. So we use a lot of static analysis and linting checks on that code, just as I would if one of my team, a human member of my team, wrote it. We will lint that code against a set of rules and requirements to prove that the code is good, doesn't have anything horrendous in it. I will review it, and we will review the simulations and the waveforms to make sure that everything is correct. And if there is something wrong with it, or there's something not quite right, or that we don't like, we'll modify it. And instead of modifying it by hand, we'll tell the agent to go away and do it. Because just like with model-based engineering, where the model becomes the master and you modify the model to generate your VHDL, with this AI flow, the AI generation becomes the master. So if you want to make any changes to the code, you ask the AI to make the changes to the code rather than you jumping in and doing it. Once we've done that, we'll take it, we'll integrate it, we'll pop it in the project, and we'll see how it goes. So we have some tenets for doing this, obviously. We want to make sure it's reliable. So trust me is not an engineering standard. I don't think it is anyway. I've seen a few people say this across a lot of time. But trust me is not an engineering standard. And we want to make sure that outputs that we're working with, that they're deterministic, that they're repetitive, and that they're reproducible. We want to make it secure. So this is an interesting point. So everything I've mentioned today, and we've been talking about, I've talked about cloud-based LLMs, Claude, Chat, Gemini, etc. But actually, you might not want to do that. You might want to have your own on-site LLM type thing for security. If you're writing a simple interface to a DAC or something like that, it probably doesn't matter. If you're writing some secret commercial IP or something that's ITAR restricted or government restricted, you're probably going to have a lot of fun conversations if you put something secret onto Claude or onto Chat. We don't assume for anything that's mission critical, excuse me, we don't assume that it's automatically safe or it's there. We take it through the exact same process, the exact same verification process that you would do if it was generated by a human. And obviously, we've still got all the knowledge and the planning and everything that goes into it. But the key message with this really is your skills and your knowledge as an engineer doesn't go away. You still need to know how to design FPGA. You need to know how to design FPGA very well. But if you're doing this effectively, then we can do better engineering, and we can do better engineering faster than perhaps what we would. And perhaps then our project managers will be, excuse me, our project managers would be a little happier. Just give me 1 second. A frog in my throat. Excuse me. So what am I actually doing? Oh, I'm treating the, oh, bloody hell. Funny thing is, I was due to give a speech the other week and my voice went. That was the biggest laugh of the lot. Anyway, I'll carry on like I've drunken some helium. So what am I actually doing? I'm treating the AI like an engineer. I'm not treating it like a magic box. I'm not vibe coding it. I'm not just picking it up and throwing it over the wall and saying, hey, give me an FPGA. That's not gonna happen. I'm not doing no architecture or no interface definitions. Hopefully one of the things that we've talked about and we've got through this is that I am actually seriously considering the architecture. I'm spending a lot more time thinking about the architecture, the interface definitions than perhaps I was previously. And I'm enjoying that more. I'm enjoying working out the architecture, the solution, the interfaces. And we're giving it all of the things. We're not giving it no data sheet. And we're not just, like I said, we're not just throwing it over the wall. We're thinking about the clocking, the resets, and whatever comes back, we are validating and verifying. What we're doing, though, is we are leading the design. As engineers, we're doing what we should be doing, which is leading that design. So we are making sure we've got the architecture correct. We're making sure that we've got the interfaces correct. And I'm a big fan of standardization of interfaces, so everything's an AXI interface or an AXI stream. We're making sure that we've collated all of the information that's needed. So we're grabbing all of the data sheets, all of the documentation for the IP cores that we might have. We're pulling all that together, the coding standards, and we're giving it to it. And then we're setting the guardrails. We've got the lint, we've got the test. So we tend to use Blue Pearl's visual verification suite in this, and we can connect that into the LLM such that it will run through, it will lint the code, it will look at the results, and it can automatically go away and check it. We can do that as a human as well, and we can go through and say, well, actually, you know, this is okay, or this is not okay, but we can go through and we can work it out. But we're reviewing everything like we would as if it was a human engineer. So I said day one, this is what we give our the agent, when we start working with it, I have a little directory somewhere on our Git tree with all of this information, the basic information about working for Duvo in it. So we give it the coding guidelines, the AMD ultra-fast design methodology, because that's actually a fantastic documentation that every engineer should read. We give it our IP and our IP rules. So here's how to create the IP that we want in our design. So how we want it, not only how we want the VHDL created, the test bench created, but how we want it structured, how we want it documented, and what we want it to look like. And then we give it the IP libraries. And this can be a little bit of a pain, sometimes trying to actually make it pick up and use the IP libraries rather than just write something from scratch. Can be a little bit of pain. But we give it our IP libraries where we've got things such as FIFOs, UARTs, SPI interfaces, anything that it might come across that it might need to use, it's in there. So we have an acceptance checklist to do this. You know, we're going to review the RTL. I don't like writing it as much as I used to, but we can still read it and we can still review it and we can make sure that it looks like we want. And this is where our knowledge and experience comes in, because I started doing this 26 years ago. I had a great start as an FPGA engineer. I turned up to my first day at the first job. They said, do you know FPGA? And we'd done a little bit on my university degree. I mean, a little bit. Maybe flash and LED or something. I'm like, yeah, of course I do. Yeah. They're like, here you go. Design us this FPGA for this radar. And then they left me to it, to go away and do it. I mean, you wouldn't do that these days. But it's good fun. It's good fun to do. So you write the RTL. You review the RTL to make sure that it's good and it's in line with your standards and what you want. We can review the test benches, the test cases that are created, to make sure that it's addressing everything that we need. And a good approach to this is we give it CSVs or data that we want it to hit. If we want it to have particular test patterns, particular test cases, we'll generate the data in MATLAB, Simulink, Python, Excel, whatever, and we will give it to the agent and say, create a test bench that does this. Create test benches that do these error conditions and this testing. And then we'll examine the utilization, we'll do a trial synthesis, we'll examine the utilization, and we'll see what it comes into it. Now, this is where that 26 years of experience comes in, because you can kind of look at the RTL, you can review the RTL and be like, yeah, this is what I would expect or sensible to expect. You can do similar for the test bench and similar for the resource allocation. You know, if something takes way more than you ever expected, obviously something's not quite right there. And then we'll run that static analysis, as I said, and run through that. So the process is the process. You know, whether you're developing it with a human or whether you're developing it with an AI, you know, it's important to have a process. Hopefully everybody here's got a nice FPGA development process. Anybody want to admit to not having one? Most companies, it's amazing, most companies I talk to, you're like, you have a process, right? And they're like, yeah, kind of, it's somewhere. We'll dig it out if you really want to see it. But the process is really key. And it's key whether you're doing AI or not, to be honest. It's really important to have a process that tells you how to go from that beginning to the end. And with AI and when we're generating RTL, we want to be able to run through that and make sure that we've got those coding standards, those structural checks, those waveform reviews, and those design reviews, for example. And what I've found is actually, this brings about a need for more discipline. It brings about more discipline and a need for more discipline in applying the process and using the process than perhaps it would if you weren't using some AI generation in there, because you actually need to actively make sure you've taken and used every step in the way. But what we don't do with this stuff, we don't generally just accept anything that's going to be safety critical or control path and just go, yeah, that'll be fine, drop it in, let's go fly in a plane that's got it on tomorrow. We don't do that. We don't accept constraints obviously without checking them, and we don't accept that the test bench is covering everything we expect. And we never stop thinking about things that are architectural. You know, so architectural things such as clock domain closing, resets, timing closure, and the design or the verification. We never really stop thinking about how all these are going to come into it. The only difference is in this instance, I've written some requirements and asked AI to write me a block. We've not asked it to write me an FPGA, we've asked it to write blocks. We might ask it to write several blocks and stitch it together to make an FPGA. But it's no real difference to, if it's done right, it's no real difference to picking up IP cores from from third party. It's just that IP code might be explicitly tailored for what you want to do. It's probably not so much good news for IP code vendors, however, though. But this is an interesting point that this brings us to, because I've spent 26 years doing this now, and I would bet from looking across the room, most of us have spent a reasonable time of years developing FPGAs, and we've done it all at the VHDL level, the Verilog level, we've seen the HLS. We've faced the challenges of how to get timing closure and such like. And this is a bit of a challenge for new graduates coming through, because they've got the AI, they've got the LLMs, and it gives you that ability to rapidly sort of go, well, I could just do this. Oops, didn't mean to do that. It gives you the ability to rapidly say, well, I could just create that module, I can do this. And they will run before they can walk. And then they will cause a huge mess, because effectively, they are vibe coding. And vibe coding is going to cause a huge amount of issues going forwards. If you know how to use it, it's architecting, it's not vibe coding. But if you don't understand the concepts, the theories, the structure behind it, it becomes vibe coding, and then it becomes a problem where you're going to build huge technical debt, or your project's just going to go out to the window, and some project manager's going to be even crying even more than they normally do. So there's a challenge. There's something that we need to think about as to how we bring about training the next generation of FPGA engineers. How do we make sure that not only do they able to leverage this level of abstraction that we've just been talking about, but how are they also able to understand that deep technical stack that we all understand as we go through that? And that comes down to everybody, one of us in the room, whether we're doing AI or not. It's our need. It's necessary for us to train and mentor and develop that next generation of engineers. So we need to think about what we can do beneath that layer. So we need to teach them the technologies about, the gates, the timing, CDC, even signal integrity on the I/O, and making sure that we can drive our signals properly. We need to mentor them. I'm a big fan of mentoring younger engineers and making sure that their work's getting structured and reviewed. And one of the big things is we need to give them interesting, challenging work. It might be fun for you're the senior engineer, you want to do the fun, really cool thing. But actually what helped me most in my career was somebody trusting me as a junior engineer to do something more fun and more cool than perhaps they wanted to do, and they just picked up some of the other tasks, the more boring, mundane tasks, and they mentored me and they helped me do that. That's how we can really help mentor and develop the next generation. We want to make them debug, There's nothing better than being an engineer than being in the lab at 2 o'clock in the morning wondering why the universe hates you, why it's never going to work, and should you have become a banker instead. But it really does teach you a lot of good skills, and it teaches you a lot of capability and brings it through. That ability to find an issue and to trace it through, and then to find the issue and fix it. There's no feeling like it in the world, right, as an engineer. When you have a problem, then you find it. It's amazing. It's brilliant. It's one of the best feelings in the world. It's only nearly as good as if it just works, and then you are really the master of the universe. But what we want to reward is, I guess coming to this, is we want to reward depth, not just speed. That ability to just generate and churn things out is cool. But in the younger generation, we need to reward not only the speed with which they can do things, but the depth of their technical knowledge, and make sure that we're generating and training them to have that depth of technical knowledge, to be able to leverage this particularly really cool level of abstraction that we have. So just to summarize here, so hopefully this has been kind of interesting, but I want to make a couple of points. One, AI is another tool. It's just another level of abstraction on there. And our goal as engineers is to use the right tool for the right job. Sometimes it might be writing beautifully handcrafted VHDL if you need that ultimate speed and you can't get there. Other times it might be using HLS or model-based engineering. Other times AI is the latest thing. It's a tool in the box of engineers that we've got to be able to pick from and know how to use. It's got some limits. I'm not going to say it doesn't have limits. It has hallucinations, stale knowledge. It can have some gaps, and it can go wrong, which is why I'm saying you verify everything. But that's no different to a human. Humans get things wrong. Humans read specifications wrong. Humans go off on different tangents. And that's why we have those verifications, those validations to check it. The cost is going to be interesting. Probably the absolute worst that the AI is going to be is today. Probably the absolute cheapest that it is going to be is also going to be today. And that's going to be an interesting thing to do. And we should plan for a world where this is not necessarily as cheap as it is today. And for a lot of applications, actually, I see a lot of customers wanting to do it on premises. You know, there's a lot of open models that can be used and that can be trained to generate VHDL, Verilog, Python, whatever. So I see a lot of people looking at on-premises solutions for their design, such that it doesn't have to go out to the cloud. It remains in their control, and they can still get the same sort of performance and benefits with it. The key thing I want to re-emphasize about this is, throughout everything I've talked about today, the weird Star Trek and Star Wars analogies and things like that, the one thing about it is that the engineer remains constant. The engineer needs to know the skills, the stack, the fundamental underlying issues of what they're working with. It's just a tool. And tools evolve, as we've seen. We've evolved from schematics to VHDL and now to AI. So with about 10 minutes left, roughly on schedule, if anybody's got any questions, I would love to try and answer them.
Yeah. You can turn on your microphone.
Nice. Okay.
Yes.
It's very impressive, right?
Yeah, it's very nice. It's very nice. So, Adam, thank you for the talk. It's very nice. However, when you say AI, it feels like you're more focusing on LLMs and usage of LLMs and the source code and all that things. And of course, we have to be careful there. But what about, for example, now AMD is introducing these engines into the fabric. And in fact, they're even encouraging developers to use these engines and write C++ and convert them into kernels. And now we have network on chip. Even they say, stop doing these AXI streams routing, just use what you have in the silicon. So you're right about abstractions getting more abstract, but what about that side of AI? Not just LLMs, but...
So that's a good question. When I wrote this talk, I wanted to focus on like using AI to develop FPGAs, not implementing AI features and inference and such like within FPGAs. I think the AI engines are fantastic, to be honest. I think they're really impressive to use. There's a great tech note, I know because I wrote it, about how you can use AI for the AI engines for DSP. And doing DSP, and you can get some really good performance out of it. And I think it ties in quite nicely with this actually, because there's nothing stopping you using AI to generate the C code that you want, or using AI to help you generate the MATLAB system composer structures that you want to put in there. I mean, most of my work with the AI engines actually has been more traditional signal processing than implementing AI. But I think they're very exciting. I think they're really cool. And the more you look into them, the more you find out about the capabilities. You know, the different types of AI, the AIML, the AI2, the AIML2. I think it's another transformative thing that FPGAs are talking about. I just had to limit my talk to something that would fit roughly 40 minutes.
Thank you.
Hello. Yeah. So my question is, should the test benches that we develop, should that be in RTL anymore? Or can we use test benches in Python or in other higher level abstraction as well?
So that's a good question. I mean, I tend to do my test benches or instruct my AI agents to do my test benches in VHDL. And typically we tend to use UVVM we use the UVVM for that. But Python, CocoaDB in Python is phenomenally popular, and is very efficient and it's very good if you're doing something that isn't perhaps wanting full safety critical, full certification type things. You know, if you want to just prove your IP blocks doing what you want it to do, then actually CocoaDB can be quite cool, because you can actually take, if you've got an image processing block, you can actually take that image processing block, use CocoaDB, grab a frame from Python, play it through and recreate it and show the image on the other side.
Yeah, I was talking about I was interested about the CocoaDB side because it allows me to create the test bench easier, faster, and with more functionality. So
yeah, I think it's a perfectly valid approach. I mean, a lot of companies use CocoaDB. I know a good friend of mine works for a HFT company, and they do a huge amount of CocoaDB in their designs just because of that speed.
Okay. Yeah.
The man up there. Yeah.
Do you use one single model, AI model, to generate the test bench and the RTL code, or do you have two separate agents?
I was wondering if somebody. Yeah, that's a good question. I tend to use one model to do that. I think there's probably an argument for using multiple models, just like you would as a human engineer. You know, it's better if somebody else marks their work rather than you marking your own homework. So yeah, I think actually having two models would be a better approach.
Thank you.
Who was first? Okay, yeah, go on.
Hi, I'm Daniel from Astron in the Netherlands. So in your concluding slide, you said that AI-based design is a latest level of abstraction on top of VHDL, Verilog, and then model-based design in HLS. Yeah. But at the same time, I see your process here heavily relies on RTL design in HLS. So it seems to be skipping over HLS and model-based design a bit. Is that a correct observation?
It's an interesting observation for this talk. I didn't really focus much on what we do with HLS and model-based design. Obviously, generally with our model-based design, we will do more verification using like MATLAB, using the MATLAB Simulink sort of hardware in the loop for co-simulation type approaches as well. But we will also, because of a lot of the industries that we work in, like the space industry, we will also push that RTL that's generated through the normal flow as well, and write test benches for it, and push it and prove it through. HLS, we tend not to use as much HLS for that sort of application. More we use HLS for sort of prototyping and demonstration type flows than we do the deliverable, shall we say.
Okay, so that also translates into you not using AI to in turn generate things with...
No, so I don't use AI to generate like HLS or to generate MATLAB models at the moment. It's all mostly based around creating me VHDL models at the moment.
Yes.
I mean, you've explained the whole process. I mean, starting from coding standards, linting, etc. But still, I do not, or from your experience, how maintainable is that code later on? If, for example, the prices spike or if they stay up, for example, how do you ensure that you can still maintain that code?
So that's an interesting point. So one of the things I do is I make sure that the LLM writes in line with our coding guidelines and our coding styles. And generally, by doing that and by giving it the structure, it's a lot more human readable and understandable than it would than other ones would be. I also push it. Some of our requirements also require it to write comments. So, for example, if you design a state machine, it will get it to draw some textual comments as to what it thinks is going off, such that we can put it in the documentation. I think I would say, because obviously I've not faced this issue yet where the model's gone or something like that, but from looking at the code, I would say it's as maintainable as it is, and the issue is as big a challenge as it is if an engineer wrote it and they left the company. I think it's in such a state that somebody could pick it up, read it, understand it, and make changes to it, either manually or ask an LLM to do it if necessary.
Okay, one last question there.
So, one for me. By the way, thank you so much for the great talk. We talked a lot about AI, and we know that some AI models speak very well on FPGAs, but that's not necessarily good for all of the models. LLMs in particular are quite difficult to map on FPGAs. So my question is, since it's an FPGA conference, where do you see the next generation of FPGAs, do you think there is going to be still the need for these specialized devices, and where?
I don't think FPGAs go away. I think they're still going to be very, very much in demand. I think you will see, like you're right. So FPGAs are great for things like CNNs and LSTMs and such like. I would not be surprised. I'm trying to how I can phrase this without violating any NDAs at the moment. I would not be surprised to see FPGAs looking at being able to at least support LLM type structures on there, because I think it's an area that they will go in. But I think, to be fair, FPGAs are probably the most exciting, fun thing in the world at the moment to be involved in and working with, because you can do everything from really simple control all the way up to crazy AI DSP stuff in there as well.
But they're also getting very, very complex.
Well, and this is why it's a chat. This is why, like I was talking about AI, and a lot of people are scared of AI. I put something on. I said I was coming here to do a talk the other day. Somebody put a comment on there saying, "Oh, I'm going to write in a paper on children and machine guns or something," and in reference to like AI being like, you know, uncontrollable. It's not going anywhere, and it's a tool that we should know how to use, and particularly because these devices are so big and so complex, that it's the only way we're going to get to be able to deliver on time. And that's what we really should be trying to do, deliver on time, because project managers cry too often when you don't.
Thank you so much.
Okay, let's thank Adam again.
Thank you very much.
Be around to answer more.
Yeah, I'll be around, yeah.
So Adam is going to be around, so I saw there were many more questions, and I don't like stopping the discussion because that's exactly why we're here, but we need to get on with the program. So you can catch him at the coffee break.